everyone. Thank you for joining us today for our UV+EB Technology webinar series. I'm Jeff Peterson with UV+EB Technology, the official publication of RadTech North America. Our webinar today is sponsored by EIT 2.0 and is titled UV Measurement 102, Proper Measurement of UV LEDs is Good Enough, Really Good Enough. Our speakers today are Jim Raymont and Darrin Leonhardt, Ph.D, that are both with EIT 2.0. And they'll be talking today. And a couple little things before we get started. You might see the question mark at the bottom of the screen. That is where you can ask questions. As the webinar goes on, everybody is on mute. But please do that if you have questions for Jim and Darrin, and we will restate those questions, and Jim and Darrin can answer them at the end of the webinar. So without further ado, I am going to send this on over to Jim and Darrin.
Hello from wherever time zone you're in. I'm Jim.
I'm Darrin.
Darrin. We subtitled this, A Physicist and a Salesman Walk into a Bar to Talk About LED Measurement. I'm the salesman, Darrin's the physicist, but we went back and forth and couldn't decide who was going to be Norm and who was going to be Cliff. It may be a reference that some of the younger folks don't get, but take a look at a Cheers episode. In terms of the talk about, just a brief introduction to EIT 2.0, why you want to measure, a little bit about source fundamentals, how they differ from mercury, how do you specify and select an LED source, measurement strategy, what happens when you have the wrong instrument, how it could impact you downstream. And then we also want to look at some real world test results. How do you communicate? And finally, wind up with questions and answers. Just a little bit about EIT. We've been doing this for over 42 years. We've sold over 113,000 different measurement solutions. These are some of our products there. We also have quite a few educational resources on our website. We did a webinar back in November that has a lot of the basics. This one will be focused on LED measurement. The team here also generates curing columns. We're up to number 28 have been posted so far. There's a lot of other things that are on the website then to help you understand UV. The way that we make a living is we have to save time, have you save time and save money when you use the radiometer. Our tools are a communication tool. What you do is it allows you to communicate within your factory. It allows you to communicate with your suppliers, allows you to communicate then with source suppliers or chemistry suppliers. We live in the world that if you can't measure it, you can't improve it. One of the things that we see with UV LEDs especially are reasons why people do not measure. Most important thing is people think that their source is so stable that they don't have to measure it. Sometimes people get bad information from their suppliers. People think that the human factors do not impact them, that their staff is so stable and so well trained that nothing's going to change in that process. They also don't allow for any thing breaking, any catastrophic failures. Darrin and I have both been in this business for a long time, and for us, it's kind of deja vu all over again. We like that the people are using LEDs. We think it's the future, but there's also a lot of new people that have come into the industry. We welcome those, but they don't maybe have the knowledge of some of the people that have been doing this for 20 or 30 years have in terms of UV. The other thing, if I were to pick on some of the source suppliers, and not all of them, but I think there's a few that say, hey, our LED is a solid state device. It's so stable that you don't have to measure it. But there's a whole bunch of other things that go on in the process in order for it to be successful that you have to track in order to get good cure. So I want to ask you if this is process control here. If you want to roll the dice, have a magic 8 ball, look at that fortune cookie, Whatever day of the week you prefer for religion, it doesn't belong in the UV lab, or it doesn't belong in UV production. And maybe some of you may want to go to a fortune teller. But any of these here are not what we would call proper process control. The big question is, what happens if you don't measure? You may wind up producing scrap. Now, this is an extreme example here, but we have heard things like this. We don't want you throwing away money. And the last thing then is you could create a manufacturing logjam. The other thing that I want to throw out to you, for all of you listening, are you able right now to describe the UV conditions that give you good quality products? This is something that customers call up. I just had a call this morning, didn't understand. They didn't understand the process window. So this is something that is critical for you. I'm going to turn this over to Darrin here for the next set of slides here.
Okay, thanks, Jim. Before we jump into the LED radiometry and other activities, let's take a step back and look at the sources, particularly how they are kind of made and designed, and then how that has ramifications for doing radiometry on them as well. We'll start with the UV LED sources, of course. These are, as Jim said, solid state devices. They come in 4 flavors: 365, 385, 395, and 405 nanometers. They have a central wavelength that, mentally is at the center of the band. If we have a 395 band, you would expect the center wavelength to be peaked about there, but the specifications are actually a little bit broader than that. It actually says that peak could be anywhere from plus 5 nanometers to minus 5 nanometers. So that peak could actually reside anywhere from 390 to 400 nanometers. Historically, LEDs have been very good giving depth of cure. Sometimes there's an issue with surface cure due to lack of short wavelengths, and then those problems are usually dealt with in terms of formulation compensation, or maybe even changing to lamp intensities as well. There's been a wide variety of suppliers, quality and support. This is something we're going to talk about in much more depth later. Industrial lamps can have a wide range of operating conditions, from many, from tens of milliwatts to many watts per square centimeter. Wide differences in energy density, which makes them a very, very attractive and useful tool in the lab. And another one of the more unique selling points is it has no IR energy, so no infrared hitting the surface. But keep in mind, if you're hitting the surface with 24 watts of UV, that's still a lot of heat that's going to be absorbed into the surface. One of the more traditional light sources, which has been around for many, many decades, is the mercury lamp. So this is a picture of an arc lamp, just as a reference. This is the other kind of stalwart or industry standard to be used. The lamp's fairly simple. It's a gas discharge lamp. It's usually put in some sort of fixture surrounded by a reflector. Bulb's energized, light comes out, and the reflector focuses the energy at a certain distance. Then you get this beautiful usual profile with the high peak intensity on the center where the focal plane is, and then you get these long wings that go on and on for a little while due to the direct rays coming out of the bulb. So that's a little bit different than LEDs. LEDs individually are very small devices, about 1 millimeter square. So the design of choice is some sort of array where many of these LEDs, hundreds of these LEDs, are put into some sort of lamp design. This gives quite a bit of flexibility to design. With a closed packed array, you get very high peak power, very high peak intensity. With a more relaxed packing and maybe a little lower power density, you could get a much larger array and produce a high dose at the surface. And this could be very attractive depending on the type of application. So what makes this very unique is power and dose can kind of be decoupled should it be necessary to help the customer get their curing done in an appropriate manner. Optically, these are a little bit different beasts than the mercury lamps. Technically, scientifically, these things are called perfect Lambertian sources, which means light comes out over a large area, at a large angle off the surface. And they follow what's called the inverse square law. And what that means is the intensity of the device drops very quickly as you walk away. So if you double your working distance, you're going to drop your intensity by 1/4. So you're going to lose basically 75% of your energy as you step out by factors of 2 in your distance. The cosine response of the device is critical in radiometry, which is how we spend our time thinking about how to address this. Again, if there's any sort of optics put in front of this thing or or molded to these devices. A lot of this goes out the window and becomes another beast altogether. So these are all details that we kind of sweat through and work through here at EIT. The other aspect I want to talk about is this single wavelength discussion and this plus or minus 5 nanometer specification. This is a little complicated, so I'm going to go slowly through this. So again, if you have a 395 nanometer lamp as it's specified, you know, the usual picture people would have in their head is that a nice, beautiful distribution of light intensity centered at 395 nanometers. Well, this is a beautiful distribution. It's fairly wide compared to the atomic distributions we're going to look at in a little bit. The full width half max here is about 15 nanometers, which is pretty healthy. And then the 5% point is reaching 42 nanometers. So this is very broad base, very broad width, but still a nice peak at 395 nanometers. Now, keep in mind, the specification of the lamp itself says this peak could be anywhere from 390 to 400 nanometers. So now the width of this distribution has gained another 10 nanometers, and the base of this distribution has gained another 10 nanometers. So we're looking at 25 nanometers to be concerned with in the middle, and maybe 50, 55 nanometers to be concerned with in terms of measuring all that light at the base. Qualities of LEDs are kind of paramount to this graph. These are industry standard lamps. These are actual measurements. This is not a simulation. These are from, you know, again, standard curing lamps bought off the shelf. We have been in contact with a lot of customers that like to buy what are called Amazon lamps, or even I love the DJ lights, as they're called. And they are, let's just call them a little bit different, a little bit lower quality light source. And these distributions could take all sorts of shapes and bumps and wiggles and very broad tails, depending on what that Amazon lamp manufacturer decided to put into the array. So you have to keep your eyes open for that as well, because that will be another difficulty for us to accomplish with. Watts, initially LEDs came out with low watts, but that was quickly overcome with technology. The watts race was on. Every major manufacturer went from 1 or 2 watts per square centimeter to tens of watts per square centimeter. So that argument kind of went out the window that LEDs could never give you the power. What we've seen in recent years is kind of the opposite. Lower power applications, which much longer exposures, much longer dose or much higher dose levels, and not so much pushing the peak intensity levels anymore. So that's, again, the versatility of the light system for the user. And again, joules are joules. It can be designed as a high watt lamp. It can be designed as a high joule lamp. It all depends on what the application is asking for. I want to put together all the spectral information in one graph to kind of keep this in everybody's mind. I know there's a lot going on here, so let me walk through it. So here we have the irradiance of the light sources versus wavelength. So the black curve here is a typical mercury bulb. It's called an H bulb. You have all the mercury lines, including the lines in the what we call the A band, which is at 365, 405, and 436. Superposed on that are the distributions for the LED light sources. Here you see the 365 lamp overlaps nicely with this mercury line. This is the mercury eye line. It's quite a bit wider than the atomic emission, but it still lies right on top of the same wavelength. 385 is kind of in no man's land between the two peaks. 395 starts to overlap this 405 peak, and then the 405 LED distribution lies obviously directly on top of the 405 line from mercury. So while there's a lot of overlap and commonality here, there's not going to be a lot of let's call it flexibility and agreeability when we start doing radiometry measurements because of the differences of the distributions. So Jim, enough of the techno talk. Why are we here again?
What we want to talk about is how good is good enough. And this is a question that you really have to answer for yourself. We do have customers that use radiometers that are optimized for mercury to measure LEDs. Sometimes they have success with those. In many cases, they get numbers that can lead them astray or lead them down a rabbit hole that makes communication within their supply chain or within their company very difficult. If you have a critical application or a tight process window, some of the differences that we see by using a broadband radiometer will be well outside of what you need in order to have good process control. You also want to be able to communicate with your suppliers and or with other company locations. Our products are a communication tool. If you're already off by 20 or 30%, 60% before you even start to communicate, you're not going to have much luck with trying to get a good quality product out the door day in and day out. We do have customers that work with multiple LED sources from different manufacturers. They're not all the same. One of the things that, as Darren mentioned, we've seen a trend toward lower power LEDs. We've also seen that everybody has the watts. People are not talking about the joules. How do you measure that? How do you determine that? What happens if you have multiple instruments or multiple locations? These are all important so that everybody is speaking the same language. You can take the wrong tool here for the job, and that's what can happen if you use a broadband radiometer to measure an LED. You can also take the right tool for the job, but maybe not use it in the right manner or the way that it was designed. So please do not try this at home, as what we say. Two main things that we want to talk about here. Number one would be dynamic range. It's important that you understand what your radiometer is doing. And the second thing is going to be the spectral response. In terms of dynamic range, this is probably our number one customer question that we get. People don't understand this. Imagine if you have a baby, you're going to weigh the baby on the truck scale here, or a baby on a baby scale, not on a truck scale here, and you're going to weigh the truck on a truck scale. So often we have people that do not match the weight or the dynamic range of the instrument to their source. So the start threshold is with the point at which that instrument starts counting the UV. There is some impact with calibration factors, but you have to start with the right range. On the low end, we tend to have a suggested operating range 8 to 10x above that start threshold. What this does is it allows us to avoid variations in the joules. The instrument's going to turn on, but the sweet spot of the radiometer is well above that start threshold. On the high end, if you take a mercury-based radiometer and try and measure a high-power LED, you want to max out. You can max out that instrument then very quickly. Best way to think of this here is Darren and I don't have a Maserati. The traffic around the area here that we're at, Northern Virginia, we're definitely not driving 185. But this is a great saying that we like from a musician. But if I bought this Maserati, I probably would not be too happy if they put a speedometer in there that went to 35 miles an hour. You're going to want to get the speedometer, the Maserati speedometer that goes up to 240 miles per hour. The way to look at this and apply this then to LEDs is our power puck, which is a broadband instrument, has a suggested operating range of 10 watts per square centimeter. You can max out the display if it's set to milliwatts at 9999.99. Sometimes you do have to switch that display over to watts. If I measure a 395 source, this is an actual measurement with one of our LED instruments at 17.4, this is what it would look like here, where we have power along the y-axis, time along the x-axis. If I were to take a broadband instrument that maxes out at 10 watts, I may lose all of this information here in the yellow. So I could underreport that. The good news is it makes that LED look very, very stable because I've maxed out that LED or maxed out the radiometer each time. But in essence, you're missing all of this information here that's shaded in the yellow.
So before we do the spectral response discussion, I have kind of a public service announcement right now. This is going back to wide versus narrow design of some of these bands. So we like to use the analogy of apples and oranges. You could have the most delicious apple and enjoy it, or you could have the most delicious orange and enjoy it. But if you really want an orange and you're eating an apple, it's not going to be very satisfying. It's still a delicious piece of fruit, but it's not what you need. It doesn't mean that it's wrong. It just means that it's different than being an apple or an orange. And the same thing kind of goes for these radiometer designs. There's a couple of schools of thought which makes both of them attractive. We go one way, of course, and others go other ways. And this is all just fine because different doesn't necessarily mean wrong. wideband response, as we classified here, is something with a very broad wavelength distribution coverage, something over 100 nanometers. That makes life simple in that one size fits all. The struggle the customers typically have is what calibration source should be used, from the manufacturer to get a reasonable reading. If I calibrate on a broadband source over 120 nanometers, and then I decide I need an LED source, that calibration is not going to suit me very well. Additionally, on the technical side, filters and optical responses of various optical components becomes very challenging to get very linear or very straight responses over those wide ranges. We've seen a lot of variations above 30% in some cases over not necessarily 100 nanometers, but even less range, where the spectral response of the band is just not as flat or not as tuned to the spectral source. And that creates a lot of confusion and even angst amongst the users. We fall on the narrow band response side of the tracks here. We focus on two basic technologies: the mercury system with the typical A, B, C, and V bands, and then of course the LED bands at 365, 85, 95, and 405. This allows us to use the specific calibration source for each band, so we have a very close proximity to what the customer is going to be using at any point in time. And also allows us to be a little more stingy or specific in our designs. We get a very good response curve. We have much better control over the optics and performance, and we're able to give the most accurate and precise results for the radiometers for UV curing. So with all that said, let's dig into the actual bands and responses that we have here at EIT. These are the traditional mercury mercury bands that go from C on the left, the short wavelengths, B, A, and V. These have been kind of standards for us for quite a few years. These are all optimized for mercury emission. We're going to superpose these along with the LED activities on another graph, so you'll see how all these curves kind of fit together, let's just say. The slight variations you see in the slopes are actually not a significant factor when these things are calibrated properly. So we have a little bit more freedom in how we choose those filters. For the LED bands, it's a little bit more encompassing here. So if you remember the discussion that the LEDs have a center wavelength of 395 in this case, and then plus or minus 5 nanometers. So we have a very broad distribution we got to cover here. So this is a good example of how we do this. Here we have a picture of the 395. Here we go. The 395 responsivity curve. The midpoint of this response curve is about 50 nanometers. So at the 50% point, that's roughly 50 nanometers wide, which is pretty wide if you remember the previous discussion. At the 90% point, we're still at about 40 nanometers, which is, again, pretty appreciable. And then when we get to the very top at the 1%, at the 100% level, we get a very flat area here, about 15 nanometers wide. That allows us to collect all the energy from plus or minus, the center wavelength plus or minus 5 nanometers, as well as capture the entire distribution of the entire lamp emission. So we extrapolate this into all the bands. You can see that these are all fairly broad bands with lots of overlap. Not surprising, of course, because these bands are fairly closely spaced. But the downside of that is if you have a 365 source, you are most likely going to get readings in the other bands as well, as should you have a 4-channel radiometer. So the key here is to focus on the band of your lamp and don't do what we call double dipping. Don't take your UV, your L365 band and then add in whatever reading you got from the 385 band, add in the 395 band. That's not going to work. The only relative measurement is the one that's going to work at the 365 band. I think I promised a little spectroscopy, so let's do it. Here we have a mercury spectrum again. Here's the irradiance or output of the bulb against wavelength. Here's the broadband filters shown in magenta and orange. You see why these filters have been chosen and sized the way they are. It covers the mercury 265 line, and this covers the 405 and 436 line pretty effectively. And there's not a lot of other activities going on between these. So these bands cover the spectral source very well, and these bands are well isolated and not missing a whole lot of activity going on with the light sources. If we look at the 395 light source, you can see that it's kind of kissing the edge of this UVV band, but it is fairly well encompassed by the the entire bandwidth. However, it's not anywhere near the center or near the larger calibration peaks of the band. So this is likely going to create some problems when it comes to doing an absolute measurement. Certainly this radiometer, the broadband radiometer, will detect it and give you a number, but the calibration is likely going to be off. And so the L395 band shown in the darker purple is calibrated exactly for this light source with the broader distribution should it be necessary. So that will do the best of both worlds. Now, if we consider putting the plus or minus 5 nanometers on top of that, again, the L395 is going to encompass the entire distribution. Whereas if we look at the UV filter, you can see this is going in and out of band in a very irregular way. So if you have multiple light sources, identical model numbers, you could literally have a 390 nanometer peak and a 400 nanometer peak, and the user wouldn't even know it if they didn't actually measure the spectral output. And then this UV radiometer would completely misrepresent that there's a problem with the lamp. So we wouldn't want that to happen. So they're out of band. The bottom line is perfect world doesn't exist, which is why we started to look at the L bands for the LED radiometers. I think Jim's ready to talk about some of the data we took. Right, Jim?
Okay.
All right.
Now, the thing is, you have theory, you have reality. We can look at the information that Darrin presented and calculate where we may be in theory, but really this is a reality test here. It really brings things home here. We did look at things here on our lab. I want to point out a couple things. The sources that we use, the LED sources that we use, were very close to the center. You can see the 365 was right at almost 368. The 385 was a nanometer and a half off. Same with 95, and 405 was pretty much right on. So we measured these with a spectroradiometer. We let the LEDs warm up. We ran them not at full power, but 70% power, 1.5 inches above the coarse window. We also have an optimized conveyor here. It does have a precision speed controller. In our calibration lab, we do not run any chemistry. We also used a fairly slow collection speed here for this test, 25 feet per minute. We don't expect that you would have these types of conditions in a production environment. So it was very controlled test here. The numbers that you're going to see that we're going to talk about, again, are probably the best that you're going to get in terms of performance. In the real world, we expect that they may even be a little bit greater than what we present here. We used 4 different units. We wanted to make sure that there wasn't any difference between the two units there of the same type. We actually set these to a sample rate that supports the 25 feet per minute. The other thing that we did is we made sure that the instruments were locked under the same area of the LED each time. Not only do we have a fixture here where the optics are perfectly lined up, they're locked into that fixture. We also made sure that with the bars that you see on the lower right, that the whole fixture was put under the LED in the same exact place each time. These are some of the steps that we do when we calibrate instruments, so it becomes very important then for us to get a repeatable reading. And Darrin, you want to talk about the test protocol a little bit? You want me to cover it?
You do the test protocol. It's your test, right?
Yeah. We did 3 runs for each individual unit. We averaged them. There was actually a total of 48 runs for each instrument. We did save the profiles, so we would have those for future reference. These are from our profilers here, where you see the irradiance on the y-axis, time on the x-axis. Not only do we get the joules and watts, but this allows us to go in and look at these very closely here. We did ignore the B as in boy, the C as in Charlie bands with this particular test. And what we'll do is go through these. I'm going to try and present the results, and I'm going to let the physicists here try and explain why we got what we got. First thing we did, it was look at how the units compare to each other, the power puck to the power puck. You can see that it matched pretty well here. It also then, in this particular example, it matched the LED then fairly well in terms of the percent difference there. When we look at the difference here between the PowerPuck UVA and the LED Cure L365 on a 365 source, you say, well, maybe I can live with 10, 11, 12%. It's not that bad. And the thing to keep in mind here, we were below the 10 watts, so we didn't lose any data because I had a 20 watt LED. It was great conditions here, but in this particular case, you could be fooled into assuming that there's more UV present than there really is. And again, these LEDs, this 365 LED was centered right at 368.
Okay, well, this is probably one of the best cases you could hope for in terms of getting good data. Both the sets of rheometers matched up really well. And that's simply because we have very close overlap between the peak of the UV LED lamp as well as the calibrated UVA band or the 365 nanometer mercury line. So the UVA band kind of overestimated by 10-ish%, probably overcompensating for the tail here because it really was calibrated with a much narrower line source than the LED is. But overall, it came out pretty good. Particularly as a relative measurement, I think we kind of hit the target in that case. How about 385, Jim?
385, we looked at both the A as in Apple and the V as in Victor. Here's where things start to get a little interesting here. The variation LED to LED, we only saw 2 to 3% variation, where we started to see in the A band 10% variation puck to puck. When we look at the actual results here, when everything was put together, we're looking at a 65% difference, where the power puck in the A band grossly underreported the values there. Again, I'm going to say the same cautionary tales here. The 385 LED was centered very close to 385. We kept it below the 10 watts. When we look at the V as in Victor, again, we're about 3% on the proper instrument. You're getting a little bit more variation there in the power puck. And it was okay here, but the thing to keep in mind is that V band could have slightly different shapes that don't impact a mercury or broadband measurement here, but it can impact greatly with the 385. And again, we're underreporting here with the power puck what that 385 LED is.
Yeah, so Jim, I think you hit all the right notes here. The 385 LED is kind of in no man's land between the two distributions for the UVA broadband and UVV broadband. The A broadband, if you guys recall, the broadband pucks actually had a large variation between them as well, 10-ish or 11-ish%. So that kind of implies that this tail is not being well recorded, but that's not what these units were calibrated for, so it's not shocking. It's basically the 385 peak is basically completely out of the UVA band. You have a large discrepancy with the actual LED measurement. It's coming into the UVV band. It's only slightly underrepresenting, which is implying, at least to me, that this is going to get kind of ugly when this UVV band starts measuring more of these LED lamps, because there's a lot of energy coming into the band, but it's not calibrated at the shorter wavelengths as well as it's calibrated at the lower wavelengths of the UVV band. So this is going to be kind of an interesting sight to see. Again, the proper LED band is well centered. You know, the peak is well centered on the LED distribution, and the UVV measurement is better in that it's picking up the light a little bit more effectively than the A band.
Okay. All right. In terms of looking at 395, this is where things start to, I wouldn't say interesting, but get scary. We've had formulators set their technical data sheets based on this using a power puck, and it gives us heartburn here. That's why we said in the description we don't joke about measurement, because it does cause serious things. You can see the power puck on a 395. There's quite a bit of variation between the two units before we even take any measurements there, whereas that L395 band is very close. And here's the scary number here, where you get up to over 90% difference with that power puck grossly underreporting the actual values there. And again, very easy to get a 395 LED over 10 watts, But these kind of numbers are not going to be good for trying to communicate or trying to save time and money when you measure. With UVV, we actually had pretty good matching with the power puck, but on the absolute numbers, the LED was reporting a little bit less energy than that power puck. That was over 30% difference here with that. So again, the numbers are not what I would use for a critical type of measurement, ones that you want to communicate, whether you're a formulator or trying to set a process window.
Mm-hmm. So again, Jim, you hit the right notes. The UVA band, effectively the 395 lamp is completely out of the band. The large discrepancies between the two broadband units, probably because this tail is a little bit different. These filters have a little spread associated with them. Calibrated out when it's used with a mercury light source, but with the LED light source is kind of showing the variation in this edge of these types of filters. UVV, again, now the peaks moved almost entirely into the distribution of the UVV band, and it's already exceeding what the L395 band is giving. So the UVV band is really overcompensating for what it's reading. Again, it's really calibrated on the larger mercury peak here. So it's not surprising that we're getting an inaccurate measurement. So as Jim said, not a good absolute reading whatsoever, but as a relative reading, that's a possibility. Keep in mind, if you're comparing across light sources, this lamp versus you have 3 of these light sources in a conveyor, they may not all be at exactly the same wavelength. So you can see this overlap here is going to be critical as to what those readings are going to look like. Otherwise, not bad. This one came out better than the previous one.
All right. In terms of the 405 LED, we did not look at the UVA. We only looked at UVV as in Victor. We actually had pretty good matching puck to puck and then LED to LED. The big thing here is the power puck made for mercury over-reported what was actually available there in terms of the UV from a 405 nanometer source. So again, you have to be careful. And we can't stress enough that we see LED sources come from good quality manufacturers that are like the ones that we used. We see LEDs where their center wavelength is 10, 15, 20 nanometers away from what's expected from sources that may not be from a good quality supplier. And then
one more spectra here. Again, looking at the mercury broadband versus the L405. Again, the LED distribution is well under the UVV, so it's being fully measured. Unfortunately, the calibration, which is not well aligned with this broad distribution, is kind of doing us in at the 40-ish% error level. Possibly a reasonable relative measurement, but as Jim said, not as a good control or recordable measurement for absolute numbers. UVA band is fairly useless at this point, not helping any of the distribution measurements in a reliable way. So UVV is at least relatively keeping up with the situation. Again, the L405 band is doing a good job picking up the entire distribution, and even has a little bit more wiggle room to boot. So this is me.
Yeah.
So if we take a step back and look at these guys, as going back to Jim's thesis, is how good is good enough. This is kind of, I'll call it the clinical, the clinical response. We did everything right. Dynamic range was appreciated. We did not overrange the puck. The measurements were done in a controlled laboratory. No chemistry, no conveyor issues. Excellent technique. Process window doesn't really apply to us. Communication, we're going to talk about that in the next slide. And what we saw was the relative readings with the broadband instrument, in some cases, particularly UVV, was pretty good. But again, should you have lamps of the same model that have that plus or 5 nanometer shift, a lot of these things will create havoc if you're not well versed in these details of how these radiometers are going to be reading, if you don't have the proper L-band filters in there. I'm a little bit more critical and say, okay, I put on my process engineer hat and say, well, okay, you guys did a great science experiment. That's great. But we got very imperfect results. The broadband instruments, more out of luck than design, have hit somewhat close to home. And there's just these large mismatches between the broadband instruments and the L-band instruments. The wavelengths shift around a little bit, which greatly affects the broadband readings. Hence, the L band readings or the LED band readings were made so that these broadband shifts weren't going to be, or I'm sorry, these LED shifts weren't going to affect the readings so dramatically as they would with the broadband. So this plus or minus 5 nanometers in center wavelength should be kind of negated for accuracy and precision for the LED bands versus the mercury bands. Again, the mercury bands, those lines are never moving, so we're very safe and confident in being able to use the L bands for the broadbands for the mercury sources. And again, some of these shifts in the wavelength of the center wavelength will go unnoticed by the user, so please be aware. Unless you're going to actually measure them with a spectrometer or spectroradiometer, depending on what your in-house equipment is, you can get very different results using the broadband radiometer if you're not careful. So please be cognizant of that. Communication. This is Jim's forte. It's not necessarily mine. Between locations and supply chain, again, you could have the same identical model LED lamp, and the wavelengths could be different by 10 nanometers, and then all of your broadband measurements can be greatly affected by those differences. And if that's not known across sites, then that becomes a real hassle for everybody. I'd like to summarize all the data here in just two graphs. I hope this isn't too busy, but let me walk through it, and I think we'll be able to kind of piece this together fairly easily. On the graph on the left here, we have the percent difference, a comparison of the broadband versus the L band lamps. So if we just look at the left axis and we look at the A band, so this is a broadband A. Remember when we had the 365 lamp, things were looking pretty good. The broadband radiometer was reading 10-ish% high, and that was because the distribution was nicely overlapping with the 365 peak of the UVA band. So we got pretty good agreement there. Jim didn't show this data because it was so abysmal, so we just left it off the chart. As this peak, as the LED lamp went from the 365 up to 405, we saw the UVA band quickly decrease in terms of what its relative measurements were, and that's because this peak quickly exits the long wavelength edge of this band and is no longer measured. However, the opposite is true for the UVV band. It started out with nothing in band. Very quickly at 385, we started to get into the edge of this UVV orange band. And then finally, at the very end, we get a very good overlap, at least with the 405 peak. But of course, this radiometer is calibrated with this narrow peak and this narrow peak, so the values aren't very good, although the spectral pickup and response is pretty good. So we'll give a large deviation up here, although it did give a decent relative approach to using these broadband radiometer for the LED lamps.
I think we want to be clear on this graph on the left that dash line is where the LED was. So anything that's away from that dash line is a percent difference, either plus or minus then. The zero line is what we'd expect a proper instrument properly calibrated to read. So you can be off quite a bit.
Thanks, Jim.
Just a couple things here as we start to wind things down here. This is more of a caution here. There's a lot of good manufacturers of products. They vary manufacturer to manufacturer. This is using broadband, but it's a good example here, whereas the EIT UVA is 320 to 390. One of our competitors has UVA from 250 to 415. They also classify different. We use a full width half max or 50% power point. The competitor uses a 10%. Perfectly fine, but you have to understand how that is established. So if you say you only have 900 watts per square centimeter, you may want to specify and say what instrument was used in order to get that number, so you're communicating in the same language. As we go up here, we do have several products. We have single band radiometers. We have 4-band radiometers. These are both available in a standard or a profiling radiometer here. We have instruments that can measure to 2048 samples per second. We have followed the trend in terms of lower power, LEDs being important. So we do now have an LED here that goes down to 4 milliwatts. So that's for some of the customers that are using the longer exposures, lower irradiance levels to measure that. We also have a fast sampling instrument, the LED Cure, or the LED map, excuse me. But with the profiler, you're able to look at things such as line speed changes, height changes, power level changes. 2 of those are shown here. We think this is critical, especially for R&D type of work. We also feel that instead of more than just a number, you're going to get the true picture here versus just the joule and watt number. We have customers in the wood industry that are using multiple types of LEDs with our 4-band LED Cure or 4-band LED map. You can look at all the different peaks here, isolate those with the profiler, whether it's 365, 95, 405 in this particular wood line. We also see a lot of digital printers that are running up to speeds of 400 or 500 feet per minute. This is actually 17 passes with a digital printer going at 400 feet per minute. We say 34 individual peaks because there's an LED on either side of the print head. So we're able to get very good resolution with this here. This is actually looking at 300ths of a second here, and we're able to get 64 individual sample points on that. So this is the type of information that gives you a lot more data than just a joule number or a watt number, especially if you have multiple LEDs.
Jim, I agree, this is really important for people that always are asking, customers are always asking for more digital data as opposed to continuous monitoring. This will give them another leg up on their data acquisition and capabilities.
Okay. So hopefully we've shared some valuable information here on how good is good enough. That's a question that we can't answer for you. But, we live by, if you cannot measure it, you can't improve it. So Jeff, at this point here, we'll turn it back to you, see if there's any questions that have come up.
Thank you, Jim and Darrin. Thanks for the great presentation. And we do have a few questions. So let's go through some of these that the attendees have asked. The first one here, monitoring medium pressure HG lamps, which produce ozone and heat. How do you compensate? Since monitoring LED UV output does not produce ozone and heat. Radiometer variance is incorporated?
So yeah, I take that one.
You want to take?
Yeah. So typically in even our calibration lab, all of our conveyors and lamps are vented to the outside. So there's a large draw and evacuation of the ozone should we be using a mercury lamp to pull it out. So it doesn't really affect any of the radiometry measurements. And most industrial settings also have a ventilation or exhaust built into their systems as well, because nobody really wants the ozone in there chewing up their equipment. So I think that's kind of an industry standard these days, but it's certainly used in our calibration and test facility.
Great. Another question, could you suggest a couple of vendors for LED UV tubes with 365 UVA?
I'll take that one. We tend to be the United Nations and work with all the different suppliers, and we're a communication tool. I think that the thing that you want to look for with any vendor, whether it's LEDs or anything that you buy, what kind of support are you going to get? Is this something that you want to put together? There are vendors that will sell a complete turnkey system with the LED array, the cabling, the power supply, and maybe integration into your line. There's other people that will sell you just the array. You buy the power supply, you buy the cables. And a lot of times it's maybe gotten better the last couple of years, but I would say LED suppliers are sometimes like the wild, wild west. We don't know if they're going to be in business a year from now or 2 years from now. So do your due diligence. There's a lot of great suppliers out there that we work with. There's some that if you do your due diligence, maybe you'll come to the same result that we have. These are people that we probably don't want to deal with for long-term support, long-term stability. So I don't know if that's a non-answer, but there's a lot of great suppliers out there.
Great. This is somewhat for us as well. Will slides be available? Just so everybody's aware that this is recorded. We will have it on the UV+EB technology website, available under the webinar link that you can watch at any time. Also, EIT will have a copy of the video in the webinar as well. So yes, there'll be several ways to be able to watch this after the presentation. Another quick question. You are giving the impression that the dose is J/M squared. I'm sorry, I'm not as technical at some of this, but can be measured, although you are talking about intensity, W/M squared. Power is, of course, important, but with a low power, you can still reach a high dose. It's a matter of time. Does that make sense to you guys?
It does make sense. I think they're probably talking, and most people in our industry curing talk about watts per centimeter squared versus watts per meter squared. The analogy that we often use is baking a cake. You get a cake box, you get the recipe, it says so many degrees in the oven for so long. Think of the temperature as being the watts, the time being the integration of that temperature or the joules. So, watts are important because they're going to give you that through cure, the punch down through the coating, and the time is important so you get the complete cure or cooking of the cake or cure of the material. So it's a combination of watts, joules, and also then matched to the proper LED type. I don't know if you want to add anything, Darrin.
The only thing is we tend to be a little fast and loose, being in the industry for a while, using our units. We say dose or exposure. In our minds, we're thinking just joules. We're not necessarily thinking joules per square centimeter. And sometimes we'll say it or we won't say it. And it's just kind of inferred from the jargon more than anything. So I think that the question is valid in that we were talking about joules per square centimeter. When we talk about dose, we're talking about total joules. And then, as Jim said, basically integrating over the entire radius profile is what it really comes down to. But we tend to be a little fast and loose, especially on a time presentation like this is how we talk about this.
If there's any questions, you can reach out to us at this UV at EIT20.com. We'll be glad to answer questions for you. Reach out to us, not a problem.
A couple others. Do you collimate the light before measurements?
So we don't have any beam changing optics in our radiometers. We will have a neutral density filter to cut down on some of the intensity, but there's no beam changing optics in our devices.
Okay. Shouldn't, for reliable process control, the UV sensor have the same measurement curve as the spectral absorption of the target?
Let's repeat that again.
I got it. Yeah.
Okay.
I would say in an ideal world that would be fantastic, but in the real world, we measure light here, and we don't create sensitivity curves or chemistries that absorb light here. And actually, we did the absorption profiles, which was on a slide earlier. You see that usually they're very low at the LED wavelengths and grow fairly large at the shorter wavelengths. But that's a whole nother webinar, I think, that we got to put on our list here, Jim.
Okay. That's the one the physicist is going to do, not the sales guy.
You're in.
If I'm running my LED unit at 300 feet per minute, what should be my sample rate?
I would definitely want to use the faster sample rate. We have 3 sample rates in our instruments. I'm talking about the pucks. The 25 samples per second, we probably wouldn't use that for anything anymore. That goes back to legacy products. The smooth profiler is 128 samples per second. I generally say when you're at 120 to 130 feet per minute or less, that's a good sample rate. Above that, I would use the smooth off, which is 2,048 samples per second. It's just a matter of getting an adequate number of samples to get repeatable values.
Great. Well, I think we're running out of time here. If there is further questions for Jim and Darrin, as Jim pointed out, the email is on your screen there. So please feel free to reach out to them direct, and I'm sure they'll be more than happy to answer your questions. Jim and Darrin, thank you very much today for joining us and for the webinar, and thank you everyone for joining on as an attendee.
Thanks, Jeff, and everybody at Peterson.
Thanks.
All right. And thank you much.
Bye-bye.
Bye.
Bye-bye.